Okay, good day, everybody online. Very welcome to this exciting panel discussion with experts from all over the world. The panel is See What I Mean, Integrating Sensing, Communication, and Semantics. I'm Rahim Tafezali, Director of Institute for Communication Systems, 6G Innovation Center at the University of Surrey. And it's my pleasure to be moderating this panel with the panelists from, I named them in the order of they will talk. Rui Yang is a Director of Engineering at InterDigital. Merwan Debba is a Chief Researcher, Technology Innovation Institute, Abu Dhabi. Henk Wijmersch, Professor, Chalmers University. Angeliki Alexia, Professor, University of Pires. So we hopefully will, all the experts will talk about different aspects of the sensing, communication, and semantics, which is known as to be one of the important features and differentiation between 6G and 5G. We'll have 40 minutes presentation, and we'll towards the end we have 25 minutes for any questions and answers from the panel, as well as people online, all of you. Please make sure that you type in your questions in the Q&A channel. So I do my best to answer all the questions in the remaining of this session, 25 minutes. Without too much wasting time, I would like to invite Rui Yang from InterDigital with this 10 minutes presentation.
Okay, thanks, Ryan. Hi, good afternoon and good morning. I'm from New York, so it's kind of early morning for me. And I'm really honored to be here in this panel discussion on wireless sensing and communication. Since I've been recently involved in the development of wireless sensing standards, so I'm going to give a brief introduction about the activities in two standards. One is IEEE 802.11 or Wi-Fi, and 3GPP. Next slide, please. Okay. So yeah, as many of you may know, that Wi-Fi market has been growing significantly over the last 10 years, and it is expected to continue to grow. The growing trends in the next 5 to 10 years. So there are many marketing research papers out there, so you can find some interesting data. As I show in the reference one, which is from the Cisco report. And here I just gave two data points, which I think is kind of interesting. One thing, of course, is Wi-Fi hotspots, right? So which is mostly used for offloading the cellular data traffic, has grown or is growing four times from 2018 to 2023, which is next year. And also when the COVID-19 pandemic started, the video conferencing traffic, which heavily depend on the Wi-Fi, has also grown more than 300% just at the beginning of the pandemic, which is 2020. So in addition, one of the reasons for the growth of a Wi-Fi market is that the Wi-Fi devices has become more ubiquitous, and they become part of many consumer electronics. Not just like laptops and cell phones, but also things like TVs, like security cameras, even like light bulbs, right? So it's almost everywhere. So basically, the dense distribution of the Wi-Fi devices basically creates the perfect opportunity to use the radio waveforms for various sensing applications. So because of this, very strong attraction, the Wi-Fi sensing has get a lot of attention from both academic research and also the industrial investments. Here I gave 2 references in there. If you're interested, you can take a look, and they have a lot of references in there to show the advancement of the sensing, the research and products. So that could be something interesting to read. Okay, move to the next slide, please. All right, thanks. Okay, so due to strong interest in Wi-Fi sensing, in September of this 2020, the IEEE working group just approved a new project, which is we call the IEEE the P802.11 BF, and also formed a task group called the TGBF. The objective of this project is to create a new amendment to 802.11 standard by enhancing the wireless LAN with the sensing capability. So the 802.11 BF will comply Wi-Fi. Sorry, the 802.11 BF compliant Wi-Fi devices will operate in the unlicensed band, which is sub 7 gigahertz frequency bands, but also above 45 gigahertz band, which is a millimeter wave. The standard will provide backward compatibility and coexistence with existing Wi-Fi devices operating in the same bands. So that's really the requirements. So the target, the publication of this standard is set to September 2024. So that's the start of the project. As far as the so when this project started, the members of task group studied several potential use cases so that Wi-Fi sensing may be useful, as shown in the slides. So basically, those use cases cover the applications from like smart home, gaming control, gesture recognition, and also presence intrusion detection, things like that. So, and those applications covers from very fine detection, also very coarse detection. So as you can imagine. Just to be clear that the 802.11 spec really covers just fine the MAC of the wireless LAN, but not applications. So we have those applications in mind, and now we design the standard to try to make them to be useful for those applications. All right, can you move to the next slide? Okay, so since beginning of the project, the members of task group had been proposed many ideas about how to enable sensing capabilities under the framework of 802.11 standards. So far, some basic terminologies and the procedures have been defined. For example, if you look at the system document there, so they define so-called sensing initiator, sensing responder, sensing transmitter, and the sensing receiver. So sensing initiator is a device which can initiate sensing, but not necessarily the device to transmit and receive the signals. But also, of course, it could also the part of a sensing receiver and transmitter. And the group also defined several procedures, such as the setting setup, measurement, reporting, termination procedures. Because this is standard, so all of those procedures need to be standardized, so that the devices with the sensing capability can interoperate together. And the waveform to be used for measure the CSI is based on a frame they call the NDP or new data packet, which have already been defined in the current standards. And those frames were originally designed or defined for channel sounding or MIMO or beamforming purpose. So now they're going to reuse those 5 frames and for the purpose of a channel measurement. And one of the important feature of for this standard will be trigger-based operation. to enable multi-sensor sounding. This is quite important because Wi-Fi is asynchronous network, right? So there's it's not accelerated network. You have defined the like subframe, frame slots, and everything synchronized. Here it's different. So so this trigger-based operation is quite an important feature for Wi-Fi. And so the figure on the right is an example of a trigger-based operation for measurement instance. So it has to start from polling the devices which want to join the sensing, and then make an announcement, which actually is a trigger operation. Basically setting the time. So from now you can start to do the sensing operation. So I'll transmit some sounding frames, and then of course after that it will be could be the optional operation, which is feedback and the reporting. Right. So that's basically things sort of activities which they have been defined, and and currently that group is still working on the specification. There's additional issues which is under discussion is feedback types. So feedback types is kind of important because it's really associated with a type of application we want to use this standard, right? So for some application, as I mentioned before, that could be very fine detection. So you need to feedback some detailed information. But however, for some of those applications, it's where you want to use the coarse detection, so you don't need to have very detailed feedback. So that's kind of issues they need to discuss. And also, of course, there's a fine MAC interface. They need to have a clear definition just for the standard purpose. And also, of course, right now it's still inventory of the standard, and they're still working on some detailed signaling and the procedures. So that's the current status. Can you move to the next slide, please? All right, thanks. So challenges, right? So there are several challenges for Wi-Fi sensing, and as I mentioned before, supporting a wide range of applications. The use cases slide I mentioned before, really wide. The people's interests are very wide. So now, how can we create a one standard to support all the applications? It's quite challenging, right? So, and as you probably heard that there's a lot of optional features in there because of the application is very wide. Right, and also we are also need to deal with the so-called backward compatibility and the forward compatibility. The Wi-Fi devices with a sensing capability are most likely a device that also can do the communication, right? So backward compatibility need to be ensured. So that's something sometimes can be dragging our feet for the new advanced technologies. Also, the coexistence with a legacy device and other radio technologies. So that's because the Wi-Fi is operating on unlicensed band, right? So right now there's new technologies start entering those bands, such as the LT, LAA, and also the new radio unlicensed. So how to deal with that is another kind of interesting problem. And the other things the other challenges is about inclusion of legacy devices to participate in the sensing. So right now there's a lot of devices in the home, in the enterprise, it's everywhere. So how to allow the legacy devices that have been used in the market to contribute to the sensing network is another interesting thing. The standard need to consider. Of course, the privacy and security is always an issue. So that's also under discussion. Can you move to the next slide? All right. So yeah. So basically, what I very quickly summarized, they introduced the standard activity in the 2.11. Here I only have one slide talking about the sensing at 3GPP. So basically, so in March this year, 3GPP SA1 started a new work item. They call the study integrate sensing and communication. I personally haven't been really participated in the contribution and also meetings over there. but I have some colleagues working in this area, so I get some information from them. And so basically, this work item will try to make sure that the sensing capabilities will be provided by the current or 5G NR, the wireless communication network. So basically, they can make sure they're not going to develop some new network for the sensing purpose. So they need to reuse the existing network. And also, there has been a lot of discussion about the communication assisted sensing and also sensing assisted communications. So that's basically, I've seen several contributions from different companies. They all talk about this. So basically, they want to have a very tight integration between the communication and sensing. So the objective of this work, this work item, is really just to start use cases and also the potential requirements for the network, and of course to identify some KPIs that can be used for measure the performance to compare the different ideas. That's basically just set up the ground for the future development. And so the target release for the standards will be release 19. I think that's probably is a 6G they are targeting at. And so a technical report will be created or released in June of 2023, which is next year. So hopefully we can see some interesting results from there. Okay, so that's pretty much what I have, and I give a list of references at the end of this slide, and at the end of this package, so you can take a look and to get more information about the activities related to standards. So that's all from me.
Thank you very much, Rui. We'll come back with lots of questions we want to ask you. May I invite Merwan for your 10 minutes presentation?
Yes, so let me
Merwan, we cannot see your presentation or hear you, if you can hear us.
this integrated feature. Do you hear me?
Yeah, but we cannot see your presentation. Okay, it looks like we lost Merwan through the bad connection. To save time, should we move to Hank's presentation and then we come back to Merwan? Excellent, thanks.
Good. All right. Thank you. Good afternoon or good morning, wherever you are. I see Merwan is back, but I guess I will continue for now.
I continue, and then I don't know what happened. Some problems of Wi-Fi, but it's okay. Go ahead.
No problem. Good. All right. So in this talk, I'll just talk a little bit about the vision for positioning and sensing towards 6G. And first, I want to clarify what I mean by sensing. So in general, sensing, if you look it up in the dictionary, it means just detecting of events or changes in the environment. But in wireless communication, sensing can be classified into two groups. So there's the more conventional non-radar-like sensing, like radio frequency sensing, carrier sensing, and maybe even weather sensing in some cases. And then there's radar sensing, radar-like sensing, like monostatic and bistatic sensing, where you detect objects and you detect them in terms of their range, angle, and Doppler. And when I think about sensing towards 6G, I mainly think about radar-like sensing. Next slide, please. Right, so this is how positioning works in 5G. So this is the typical way of doing it. This is shown here in uplink. So a user broadcasts a signal to several base stations. These base stations are tightly synchronized. They measure the time of arrival of the signal, compute time differences of arrival, and based on that, they can constrain the user to lie on the intersection of hyperbolas. And this is really limited in terms of the base station deployment and also the multipath that affects the accuracy. And then in 5G, you can get accuracies maybe down to 10 meters. There's reports of down to 1 meter, but it's really in exceptional circumstances. And in 5G, there's no radar-like sensing defined at all. So this is something really new towards 6G and 5G advanced. Next slide, please. So what will 6G bring for positioning and sensing? So these are two figures from different sources. The figure on the left comes from a colleague from Spain, where you see on the x-axis the different uncertainties for positioning, on the y-axis the deployment environments. And you can see that, for instance, in rural environments, GNSS can provide very, very high accuracy because you have access to lots of satellites and maybe site information to do carrier phase positioning, while the typical cellular signals, 2G, 3G, 4G, and 5G go down to 1 meter in some cases. And there's this big gap for indoor and challenging urban outdoor environments where you maybe need very high accuracy, but no technology can offer it. And there's now the vision that 6G can offer this very high accuracy, so both indoors and in urban outdoors. The figure on the right is a picture from a paper from Nokia, where they talk about, well, that positioning can achieve much higher accuracy due to a combination of different technologies and new features towards 6G. And I will talk about those in the next slide. So next slide, please. Maybe you can click through the whole slide. It will be a bit easier. No, sorry, there's a lot of bit more. Okay, yeah, thank you. That's it. All right, so 6G will bring a lot of things. Some of them are already present in 5G, some of them not. So I will just quickly walk through them, and then I will go through some of them in a bit more detail in the following slides. So first of all, a wide variety of carrier frequencies. So not just FR1, FR2, but also maybe D-band frequencies. And each of these bands has different uses for positioning. So it's not so that, you know, only millimeter wave or only D-band will be used. The lower frequencies have a big role to play as well. One thing that's really important, that especially at higher frequencies, larger bandwidth. This provides high delay resolution, and resolution in general, whether it's through delay or angle or any other means, is the most critical thing, I think, for having high accuracy positioning and sensing. Otherwise, you will always be limited by multipath. Third is to have a large number of antennas, especially at higher frequencies, to overcome the path loss using fine beamforming. And these large number of antennas provide you high angle resolution, the ability to estimate angles of arrival and angle of departure with high degrees of accuracy. Fourth is the introduction, or the reintroduction, I should say, of side links into standardization. So links between devices, you can think of links between cars or between cell phones. And this will open up relative positioning capabilities as well as radar-like mapping capabilities. Fifth is network densification, so having high degree of line of sight connectivities, and in particular cell-free massive MIMO, which I see as something kind of new in the positioning field and sensing field. Lots of new interesting questions and opportunities there. Sixth, already mentioned by the previous speaker, the integration of sensing, localization, and communication. Seventh, the more widespread use of AI. I'm not in favor of applying AI everywhere, but there are some kind of critical problems where AI can really shine. And then the final one is the use of intelligent surfaces or RIS, which can help improve positioning. And I think the last speaker will talk about that more. Among the main challenges that I see, one is the lack of channel models at those high frequencies, and also coherent channel models across different frequency ranges, which are needed for positioning and sensing to stitch things together across different frequencies. And then hardware impairments, especially at higher frequencies, will be really very important and will be much more severe, I think, for localization, sensing, and for communication. And then finally, something that is often forgotten in academic research is that to get extreme performance, you need extreme calibration. Right? A small error in the tilt of a base station panel will lead to very large positioning errors. Next slide, please. So in the next 5 minutes, I'll just talk about some of these in a little bit more detail. So the first one is the use of monostatic sensing. So the figure on the right shows how monostatic sensing works. So the vehicle on the left is broadcasting a signal, either a side link signal to another vehicle or an uplink signal to a base station. And then the backscattered signal can be processed to figure out where objects are in the environment in terms of their range, angle, and Doppler. And this, of course, requires full duplex transmission, which is really challenging, but needed for supporting this monostatic sensing. There's different ways that you can do this. So you can use the same hardware, of course, for communication and for sensing. You can also use the same waveform for communication and sensing, or you could use different hardware or different waveforms for communication sensing. And it's not really clear what is the best solution right now. A lot of the research that's been going on is really on using the same waveform for communication sensing. And then you can play all kind of trade-off games. And this is what's shown in this figure on the right, where you, for instance, do power allocation, OFDM, and then you can have kind of communication optimal operating condition like water filling or radar optimal condition. And then, of course, the communication will be degraded. When you use separate waveforms, then this is not an issue, but this is maybe more promising for meeting, for instance, safety critical applications. Once you have sensing and communication with sensing and localization with high accuracy, there's lots of cross-functional benefits, right? So you can, if you know where something is, you can point a highly directed beam towards that user, and this can speed up things and reduce overheads. Next slide, please. While monostatic sensing has been getting a lot of attention, we should not forget there's also bistatic sensing. So if you think about standard localization, it's a form of bistatic sensing, right? So there's a base station emitting a signal to a user. The user receives the signal, but the user receives the line of sight signal shown in green, but also the multipath signal. And this multipath signal can be used both for improving positioning if it's resolvable, and this is why you need high resolution, or to map the environment if the user position is known. And the nice thing is that, well, for instance, you can do single base station positioning if you can exploit a multipath. You can even do positioning when the line of sight between the base station is blocked. So these are all kind of unexplored possibilities to be able to do positioning and sensing with really minimal infrastructure. And of course, one of the important things here is that in standard positioning, base stations need to be synchronized, but here when you exploit multipath, the synchronization is somehow provided to you by nature. Next slide, please. Next. Right, another underexplored opportunity is to do per user signal optimization. So right now, the signals that are used for positioning or the positioning reference signals are broadcast signals. They span the whole frequency band, they span over time, and they also have a spatial dimension. But once you know a little bit about where the user is, you can really optimize the positioning signal for each individual user or groups of users. And this can boost performance a lot. You can provide a lot of service differentiation, and of course, operators can charge for that to provide high accuracy sensing and localization for those services where it's really needed. Next slide, please. As I mentioned before, so AI, I think, can play an important role for solving some of the problems that we have at different layers of the protocol stack. One of the things where I think AI can really shine is to overcome hardware impairments. And this is an example from a paper that we did where we do an autoencoder for joint radar and communication in the presence of hardware impairments. And the figure on the right shows, for instance, the detection probability, which is a radar metric, and the symbol rate, which is a communication metric. And there's a trade-off between the two. So depending how you optimize the system. And this by itself is not very interesting, but on the figure on the right, we put hardware impairments in the mix. So we for instance, perturb the antenna locations, and then the traditional methods fails, right? Because the traditional method thinks everything is perfect. But then using data-driven methods where you just learn based on the data can then improve performance a lot. Next slide, please. Yeah, something that will be touched upon by the last speaker is the use of intelligent surfaces. They've been talked about a lot for communication to overcome line of sight blockage, have lots of very interesting features, but I think they will really shine for positioning and sensing. They have really unique capabilities to replace base stations, to exploit near field effects, and to also to serve as kind of intelligent scatterers that can be detected really easily with radar, with standard radar. So lots of untapped potential there as well. Next slide, please. Of course, there are lots of challenges in enabling all of these, using all of these technologies, for instance, hardware impairments. And I see that I'm running out of time, so I will wrap up. But I think, yeah, there's different ways of treating hardware impairments. So here are some of the examples: coupling, nonlinearities, in-phase and quadrature imbalance, and so forth. And the standard way is for us to ignore them, but I think there's new methods that we need to do to mitigate them, which are different from those used for communication. And in some cases, we can even exploit them. And that goes down to my last slide, I hope. Right, okay, so I think there's lots of untapped potential, even in 5G, lots of promise towards 6G. I will not read through the whole slide, but I've been working on radio-based positioning for over 15 years now, and I think the golden age of this has really just begun. So it's a very exciting time for this. Thank you.
Thank you very much, Henk. It's full of and rich in information. We'll come back to it towards the end. Let's go back to Merwan now. I hope your Wi-Fi link is all right.
Well, what I did is even better. I switched to my 5G link, so then I don't have any issue anymore. And it seems that 5G is much more reliable than Wi-Fi, so that's a good sign for the future.
It's good to know.
So as I was saying, I've been working at the interface of 5G, 6G, and machine learning. And I think I accepted to be in the session because I think a lot of the work on sensing and communication.
Merwan,
will-
you're not showing the right slides. If you're showing your email.
Okay, that's weird. Okay, let me just do a D-share and reshare.
Yeah.
Okay. Good. Now is it good?
Yeah. Yes.
Very good. Yeah, so as I was saying, one of the reasons I accepted is because I think that a lot of the work which is being done in the future will be, especially in the sensing and communication, will be around this classification. And of course, a lot of the techniques that we use in machine learning are based on this. So before, of course, I start, I think you're all familiar with the evolution of the generation. And I think with already 5G, we saw a differentiation with the classical, I would say more data, or basically the classical approach of more bandwidth in the Shannon sense, with this triangle related to MBB, massive machine type of communication, and URLC, where we didn't have any more one target, but roughly 3 targets. And I think the same kind of things is happening also in 6G, where basically the kind of targets are going to be of multiple type, and for which basically the waves are going to be used in another manner than just sending bits. One of the manner, of course, of the session is related to sensing, but of course we have also manners related to providing energy, wireless energy transfer, and other things like that. But before going to 6G, we have to have in mind that there's already work going on at the moment in the evolution of what we call 5.5G or 5G advanced, and in which already the issue of communication and sensing, not to its limit, is already there. So today, there's already a sort of a definition of 5.5G, which goes from the classical triangle to this hexagonal, which is adopted by roughly many companies, especially Huawei and others, and for which basically the idea is the combination of all these points that you have in the triangle, because they're hard to get. The first one is what we call RTBC, where basically you want to have at the same time broadband with reliability. Now, as you know, it's very hard to have that operating point. And many people have been working on what we call the diversity versus multiplexing trade-off, because whenever you have more diversity to get this reliability, then you lose in terms of bandwidth. And this is something extremely hard to get, especially for this holographic type of communication. The other is, of course, the uplink-centric broadband communication in terms of getting more data in the uplink. And uplink is a big issue today because of the fact that in general on the device, you have only one antenna. And basically the power at which also these devices transmit is extremely complicated. And today with the multiple number of cameras that we have a massiveness of devices that want to transmit a lot of data in the uplink. But what's interesting is the combination that we're seeing in terms of providing more and more what we call positioning. And positioning has become a big market. It started already in 5G a bit with narrowband IoT, where basically there was a lot of bikes in the market and people wanted to have the positioning, and that would come as a service. And today positioning is coming with LiDARs, and this is something already kicking in 5.5G. But now in the 6G realm, we're talking about something much stronger. And the idea, of course, that we're all coming up with is the fact that we want to have a better perception of our environment. Why? Because basically you want to have some kind of super resolution of your environment in terms of distinguishing two objects with a kind of minimal, basically, distance that you can do. And there's, of course, a lot of reasons you want to do that is because you're tending to have what we call here mobile for machines or in the future, and for which these things need to move around and they need to position themselves. The other, of course, is the classical holographic type of teleportation, where you want to have senses which are transported from one point to the other point, and for which you need to have a very good accuracy in terms of positioning on one point of the communication link to the other point of the communication link. Now, the question is why basically it's happening today. So, of course, the reason why it's happening today, and there's a lot of work going on, is, of course, the fact that thanks to the fact, and this is physics, that we're going into higher frequencies, this is classical, there's something called the wavelength. And the more you go in higher frequency, the shorter is the wavelength. And the wavelength basically tells you what is basically the kind of accuracy with which you see your environment. So the more the lambda is smaller, the more you can distinguish object within your environment. So we have a great opportunity basically to be able to do reconstruction. So by doing reconstruction, we can do it at two levels. One is what we call terminal sensing, and basically seeing hidden objects behind basically walls, being also to do some kind of full spectral sensing analysis, and also all the problems of vehicles around that. And then there's another thing also that I think we haven't exploited enough is infrastructure sensing. And infrastructure sensing, meaning that basically we're able basically to be able to reconstruct our environment, the texture exactly of the walls, and then build up better schemes in terms of transmission, because we know that there's concrete there, there's some kind of glass there, and basically we can reconstruct and rebuild some new kind of opportunistic physical layer thanks to the fact that the base station can see the environment around that. And of course you can do that because you start playing with analytics because of the kind of waveform. So the kind of waveform that you can use, I don't have no clue what it is. Of course, a lot of people are using for the integrated sensing and communication realm at the moment, classical waveforms that have been used in 4G and 5G, and even in terms of research. What I mean by that, using OFDM, using OTFS, and looking at its performance. But I think we haven't touched upon the problem of really defining what is the kind of best type of waveform which could go within that realm. There are types which have been already defined, which are what we call spheroidal functions based on Slapian work in the 70s. But there, we don't know how to construct them in a digital manner. It's mostly continuous. And this is a bit of an issue at the moment in terms of research of what you can do. And of course, also, let's say more at the network level, we've been talking mostly about sensing assisted physical layer, where there's the air interface relative sensing, the exactly also kind of reality mapping and judging and beamforming. But you have also some sensing, I would say, architecture that you can build at the network level. And I think also the kind of work that the network guys are doing has not touched upon the fact that there's a great opportunity now to also define a clean slate network architecture, not just physical layer, with the idea behind of maximizing some kind of utility related to sensing. And this goes to what I call here the different of traffic reconstruction, network planning that you can do at that level. And again, as I said before, the kind of opportunities are not just related to just smartphones. All the industry will be touched upon, going from millimeter wave radars to lidars that are equipped with cars and all these objects. And this goes also to the fact that we have this opportunity of moving more and more in higher frequencies. Now, of course, there's still big discussions today in terms of if 6G will be a terahertz, I would say, kind of landscape or a millimeter wave. As you know, a lot of people thought that 5G will be millimeter wave. It turns out that 5G turned out to be extremely difficult to deploy millimeter wave, especially in the mobile scenario, to do what we call the beam alignment. And many people think that will be pushed back more to the 6G and terahertz will be going on. But still, the fact that we're going in higher frequency and millimeter wave will be a big part of 6G, will provide us the opportunity to have the super resolution that I was talking about at the beginning. And that's basically in terms just of the capability of reconstructing your environment. The second point also, which I think is important, is the fact that with all these opportunities of going towards terahertz, we need also to relook at how we used to do communication, since the idea of transmitting just bits is not anymore there, and especially in transmitting bits in a full range of long network. And basically what the idea today is really about not moving anymore the data within the network, but moving basically what we call the computing within the network. Of course, the realm of computing is just the fact that by moving the models that you learn, well, you can do some kind of compression. And this goes, of course, in the big realm of semantic communication and all these ideas. Now, you can ask me, why can't you do this within the realm basically of the classical, I would say, sub 6 gigahertz, and why would it be something quite linked to the fact that you're using higher frequencies and terahertz? Well, there is, of course, an opportunity because there, as you know, the communication link turned out not to be extremely reliable as it is. And we have great, I would say, compression opportunities by leveraging from the computing capability that we have to be able to be more predictive in how we do their communication, but also compress our information and define other realms in terms of targets. Because at the end, when you do sensing, the objective is not about just sending bits towards somewhere, but about inferring on a certain parameter. And inference is all about all these ideas of computing, because when you want to infer on a position, then basically you start doing techniques like AI-based localization, for example. And this is where the computing starts going on around your network. And of course, how you build this kind of joint sensing mechanism, which is related to inferring on a parameter with respect to the global architecture, is still open, because it's still not very clear where this kind of activity of sensing will be done. Will it be done by gathering all the data and going on in a given, I would say, more centralized place? Or you're going to be doing it more in a distributed manner in terms of doing what we call distributed sensing with all the small data that you gathered and how you start compiling it to start this reconstructing your environment. The last point I think has been touched upon by my last colleague right now is, of course, basically that we still have some issues related to the fact that we still want to send data, because it's this sense of integrating sensing and communication. And the problem is that if you want to sense, you want to go to higher frequencies to get the super resolution that I was talking about. But on the other hand, by going in higher frequencies, then the kind of coverage that you get is very low. And the question is, how can you get still that capability of doing sensing at a very large distance and being able still basically to get this capability of communicating? And there, it was touched upon my colleague. We are, of course, in all the community have been jumping in new opportunities that are offered by the fact that the channel is not anymore an independent entity from the TX and RX, but becomes part basically of the communication realm, where we can basically do what we call a controllable environment by modifying the texture or the properties of your environment to provide better opportunities in terms of communication, irrespective of the frequency that we're using. And there's been already some experiments showcasing that at millimeter wave, you can, of course, increase the coverage in a very drastic way by using techniques coming from the large intelligence surfaces, reflect intelligence surface, smart environment, smart wireless, whatever you call it, that of course provides you this enhanced coverage of those frequencies and those opportunities to sense with a longer or more broader or in terms of range at which you communicate. I think I gave you here the main ideas related to what I think are the possibilities of this integration and sensing and communication. And I look forward basically for the panel discussion to answer questions from the audience.
Thank you very much, Merwan. We move straight to Angela.
Thank you. Let me try to share. Right, so thank you, Rahim, and thank you for the invitation. This is really an interesting discussion and panel, and being the last one, you know, it's good and bad. It's good because I think the majority of the points I want to make are already there and explain. So that's good. But at the same time, I think I still have this opportunity to summarize and maybe even present to you a selection of key takeaways. So I will try to do that in the next 10 minutes. So what I wanted to do in the next 10 minutes is to first of all explain the list of let's say opportunities that terahertz as a new radio, if you want, approach brings into play for 6G. Then use as examples two system concepts that are based on terahertz wireless, and also try to synthesize important enablers that seem to be promising for what's coming next. And finally, you know, conclude with some, let's say, warnings or promises at the same time. So the terahertz opportunity, I think it's been clearly explained, and I'm happy to see that all the speakers basically seem to be convinced that this is a real opportunity that mainly comes from the fact that a huge amount of bandwidth is now becoming available. So this unexploited new land not only offers, this plethora of resources, but also opportunities in terms of usage scenarios that are now becoming possible. And this was also evidenced already by means of millimeter wave that brought into play, for example, the opportunity for high definition for AR, VR, etc. So as an evolution of a 5G. So going orders of magnitude higher, now we are really in a position to say that this new frequency regime opens up a new dynamic range of opportunities that are not limited to communication and expand to sensing, to localization, navigation, etc. Just to make a point on the propagation, there is always the usual argument, and I don't think it has been that much discussed in this panel. Propagation is also, I would say, an opportunity here, because except for the path loss issue and the fact that we need to understand, the link budgeting issues that terahertz will bring, it is important to see that terahertz stands in a sweet spot, I would call it, between the two extremes. On the one hand, microwaves that offer, specular reflections, and also the higher frequencies, for example, the optical frequencies that are characterized by diffuse scattering. So in the terahertz regime that stands in between, one can have, let's say, the best of both worlds and exploit it for the different needs in terms of propagation and in different usage scenarios. So the third, let's call it opportunity, is that of opening up new dynamic range of applications of the kinds of cognition, sensing, shaping, and shape identification, imaging, and positioning that seem to be so important in the coming 6G usage scenarios. And I will spend maybe a minute later to comment on that. The fourth opportunity, which I think from my point of view is probably the most important, and it is really the accelerating factor of terahertz, is the opportunity of empowering wireless technologies that we have studied in the past, but that are now, that have their chance to shine. I'm talking about pencil beamforming, massive MIMO, reconfigurable intelligent surfaces, holographic radio. So with such small wavelengths, there is now the opportunity to really go to a different scale of implementation of these technologies. So I think this is really an obvious accelerating factor. Let me then use maybe only 2 or 3 minutes to explain two, in my view, two important terahertz-based system concept. So the first one, extrapolating, let's say, on the powers and the capabilities of terahertz, is what I call fiber over the air. So the idea here is to create a wireless network that is of the same reliability, of the same robustness, and of the same capacity as in the fiber case. This is important to be able to talk about inclusion, sustainability, extending broadband in remote areas, also enhancing broadband coverage everywhere, and at the same time also covering shorter range scenario, like, for example, indoor AR, VR cases. But one has to recognize fundamental characteristics of terahertz. Most of them were mentioned before, so I think I will really go fast on that. Loss being one, dependence on humidity and other weather conditions being another one, dependent bandwidth. So a new information theoretic framework needs to be understood and studied. And last but not least, what I call directional terahertz, pencil beam based terahertz, requires a lot of sophistication in terms of tracking of users and aligning the beams. So blockage, misalignment, and tracking are the major challenges in this new radio environment. And only if there are inherent design of and inherent consideration of such challenges in the radio, including physical air and MAC, it is only when one can really deliver this fiber over the air. So these are some examples that show the visibility, let's say, of terahertz wireless connectivity that have been implemented a few years ago. This is an indoor example, and this is an outdoor long range example. The second concept I would like to talk about, and I think this is mostly related to this topic that we're discussing today, is this what I call beyond Shannon. So here terahertz is the basis that enables the synthesis of three important concepts. The concept of reconfiguring the environment, what we call beyond Shannon, in order to jointly design transceiver and channel. The concept of using intelligent materials to be able to materialize the beyond Shannon concept, and also the concept of really optimizing the combination of beyond Shannon principles with intelligent materials with the help of machine learning. So I think this takes what terahertz radio to a step further, offering important properties that those of self-healing, reconfigurability, and learning capability. So just to give you a very basic example of self-healing, which is just only, as a proof of concept, let's say, that can be extended to include major enablers. The idea of self-healing is to be able to really reconstruct the beam, even if there is a blocker in front of it. So we want to do that at the physical layer, it's shown here. We would like to do that using reconfigurable intelligent materials also. So let me just keep these results that talk about reconfigurable intelligent surfaces and their capability to optimize coverage to account for blockage by means of optimizing their position and orientation. And give you another example of why machine learning will be so important. So think about it, that you have three levels, let's say, of degrees of freedom. You have the level of reconfigurability and self-healing at the physical layer. You have also the level of optimizing these capabilities at the system level by optimizing positioning, by optimizing orientation, by optimizing RIS, programmable RIS. And you also have the ability to optimize at the network level by employing machine learning and artificial intelligence algorithm. Like in this example, there is a clustering approach to blockage avoidance. So you see, the synthesis of all three, I think, are of paramount importance for what's coming next. And as a final concluding remark as to what is coming next, if I had to also summarize main trends that have been explained today in this session, I think we need to put on our list not only the problem of inclusion and global connectivity, but also the importance of immersive connectivity. So the capability of really having an environment that responds in an agile fashion by configuring itself. The also capability of intelligent connectivity to account for mobility, for ad hoc topologies, and last but not least, the ability of the Internet of Senses that based on fusion, based on localization, also offers the possibility to use 6G as a way to really integrate senses and sensing into communication. So this is a schematic that discusses these principles of inclusion, immersion, intelligence, and sensing in the framework of pencil beam-based terahertz connectivity for the various scenarios. And I think maybe just as a final remark, I think the important and challenging and exciting part of it is that we are now really in a position to exploit the integration between different angles of technology, not only radio advances, not only materials advances, not only computing and learning advances, but I think the synthesis of all of it will be accelerating by the inclusion of sensing. And I think there is a lot of beyond Shannon discussions. And someone told me the other day that, well, maybe this is, too much. I think the important consideration of Shannon 1.1, 1.2, or beyond Shannon is to go back, look at the initial statement that talks about the technical problem of delivering correct bits, accurate bits, that talks about what it means to look at the semantics problem and effectiveness problem, but really advance these definitions to what is important today. So to the KPIs and the KVIs of today that include energy efficiency, cost efficiency, sustainability, etc. So I think it's even beyond Shannon 2.0 here. I think it is about redefining these principles. And I believe that sensing has a role to play here. With that, I will stop. Thank you.
Thank you, Angela. Thanks very much. Let's get everybody back, all the presenters. And please, everybody's online, type in your questions in Q&A button. And I try to ask those questions from the panelists. To start, thanks very much for very interesting presentation talks. May I start with asking a question? I think, Mervan, you mentioned Shannon 2.0, and Angela, you said beyond Shannon limit. Can you say that in 6G or 2030 plus, whatever you want to call it, 5.5G or beyond, are we gonna have a different Shannon capacity limit or equation that we have to deal with? What do you mean by that? Shannon 2.0 and
so that's a good question. No, the Shannon limit will not change because it has been devised by Shannon. The idea of this Shannon 2.0 comes with what we call this level B type of communication, which was devised already by Shannon in one of his book with Weaver. And the idea basically is, on the contrary, that the notion of when you start having the capability on the model to store the data of your past communication, which is not the case when we do today. When we do today, whenever you start a new communication, you start it from scratch. So there's no past experience that you take into account. Well, there, what you build is some kind of context that you build between a transmitter and receiver. And by building a context between transmitter and receiver, which is what we do as humans, the more you talk with somebody, the less after you need to talk after to have the same kind of goal. Then basically you have what we call some sort of compression rate, which happens because you need less bits to transmit to get the same impact. So in terms of getting more bandwidth or more capacity or more bits which are transmitted, this is not what Shannon 2.0 is going to make you happen. at all. So it's going to be more about basically having less number of bits which are transiting. And second, also, which is very important, is that we are in a society where we think that what we need to transmit is basically the data. In fact, what you need to transmit is the model that you learned, because on the other side, if he has the model or he has the knowledge of how you think, then basically he can converge better into some kind of common understanding. So the idea also here, which will happen, is that it's not anymore the data which will be transiting in a network, but it's going to be more about the computing which will be transiting, which is also basically what's happening in the, by the way, in computer science industry. In the computer science industry, you have to know that they're trying to rebuild the what we call the von Neumann architecture in terms of computer, because the von Neumann architecture was based on the fact that you have data, it go to the computing unit, you get the result, and then you store it back. And now they realize that this is transition makes you a lot of loss. What you need is to bring the computing where the data is. Yeah. And this kind of change is going to happen. Now, for your Shannon capacity, this is another issue. And I think what Angeliki was mentioning about and others, there, I think the realm is more about, if you want to change the capacity, you need to change the model of your environment. And one way that we're seeing today of changing the model of environment, which somehow is easy instead of moving the buildings, is to basically change the texture of your environment. And by changing your texture, you change the properties of reflection. And this is now a very neat way through this notion of metamaterials, which everybody's jumping about. But I think this is only one way of doing it.
Yeah, no, thanks. Angela.
To summarize, I think Merwan covered everything, but just to summarize, what is beyondness, right? I think beyondness is threefold. The first one is that what is system? So in the conventional theory, system is transmitter, receiver, and channel. But now in the beyond case, environment is part of the design. So RIS and intelligent material help with that. So system is different. That's first. Second is what is information? So not any more bits. Shannon and Weaver in the book also explained that, but semantics comes to redefine what is information. And the third, and maybe more challenging, is what is performance. So capacity is there and all Shannon limits are there, but we're not sure if this is the main point, the main KPI we want to cover.
Well,
that's beyond.
Yeah. This is a question to all of you. We talk about communication and the importance of sensing, and we said that it would enable many applications, but not only applications in terms of services and etc. from the user's point of view, but also it would help the network to operate better with the protocols, with the algorithms, and that's so I think that was Merwan asked. My question is, are we going to have two different waveforms, two different frequencies, one for communication, one for sensing, or is it the same waveform doing both things? Let me start with Rui, probably.
Yeah, thank you for the question. This is kind of interesting, right? So as you can see, from both 3GPP standard and also the Wi-Fi standard, right? They all talk about using the same network, same resource. Maybe from the industry perspective, right? Because the spectrum scale is expensive, and people don't want to, either take a chunk of this resource for the purpose of sensing only. Right, so people still want to really just reuse the existing network and resource for the purpose of the joint sensing and communication. I think that's the mainstream.
Would that limit the information we can sense if you use the same waveform, for example?
Well, definitely. I mean, there's no free lunch, right? So if you take some resource out for some purpose, and then the other one will suffer. However, I think something need to be smart here is because just like in old days, so we talk about the like FDD, the downlink channel bandwidth is always congested, but the uplink is more open, and how to smartly use the the resource to slide the resource differently for different purpose. I think that's a kind of a trend we'll go into to use the same set of resource for different purpose. And during the process of doing this sensing, the studies, right? So actually, when we talk about applications, right? So communication is a application for sensing, if you want to look at it that way, right? So you can look at this more broadly for the more from application perspective, and sensing just provide a measurements, and how those measurements will be used for different application, and of course communication is one of them. So I think that's probably the way you can look at the whole thing more broadly, not just focus on sensing versus communication only. Yeah. That's really the way I'm thinking.
Yeah, is helping each other. Hank, you mentioned that on the positioning side, you mentioned that there is device impairment is the biggest problem, is the biggest challenge, and you said that multipath, if it can be resolved, it helps, and etc. Does it mean for positioning we need to have a different waveform than what we have in 5G for 6G?
Well, typically in positioning, we've always tried to reuse whatever communication waveform there was. So, and I think this probably will remain the case. However, the waveform to me is just a template, right? You can fill it in how you want. It's an OFDM with some numerology. You can still optimize power allocation, beam allocation, optimize the heck out of it for positioning purposes. So I don't see that there will be a special waveform, it will be further optimized to improve positioning or sensing performance.
Yeah, but if you had the freedom to change it, what would that be?
Frankly,
forget about legacy and backward compatibility.
No. I really wouldn't care. I really wouldn't care. I think what to me positioning and sensing is all about is about resolution. So as long as I have the total bandwidth available, phase coherent, I have large antenna aperture and a sufficiently long integration time, I don't care if it's OFDM, OTFS, FMCW, PMCW, whatever you want, I don't mind. It doesn't really affect the positioning quality very much. Of course, some of those waveforms are more hardware friendly than others.
Okay, we have lots of questions. I wrote down lots of questions, but we have about 2 minutes left. So I try to ask questions that been asked online. First of all, I think that one of the questions is asked by Mitch Singh, I think online, says that with sensing, with the communication integration between them and a whole raft of new services and etc. from the user's point of view or network point of view, are we going to see in 6G era a different communication than the smartphones that we have? Are we going to have the smartphone the main point of contact between us and the network? What's going to happen to the smartphone? I mean, that's what it is. Do you want, Marwan, do you want to go first? And then I'll go across the screen.
I can go first. Of course, this is not an easy question. I don't think the intention of 6G is really about a smartphone. It's really about, we connected basically humans, we connected things. Here we want to connect machines. And I think there's going to be more and more by the year 2035, machines surrounding us, and for which they will be starting to communicate, and for which basically the kind of latency, things like that are there. So it's much broader than just a smartphone or whatever device that is able to help the people communicate will be there. So of course it could be the glasses that Google is working on, and others, Apple. But I think we're talking here about 2G mobile for voice, 3G mobile for data, 4G mobile for internet, 5G mobile for things. And then here we're talking about mobile for machines or mobile for intelligence. And by going on there, then the gates are quite open on all the objects which could embed that kind of intelligence, and machines are part of that.
Yeah. Anybody else want to add?
If I may,
yes,
not forget, V2X, V2V, drones, and other usage scenarios that are not, we're not used to. I think this will be also important characteristics, features of 6G. So there's more than smartphone for sure.
No, thanks, Angela. We have about 30 seconds left. Is there anything that you would like to add in these 30 seconds? Anybody, from Hank, Rui, that you want to, the last word, I give it to you.
Yeah, if I may can give a last word. So I think there's one slide I noticed from Dr. Debar about this, the neural networks on both transmitter and receive side, right? So basically, the AI ML will go into this area by all means, right? So, but the sensing is, I think, it's a pretty important part, because the old AI ML stuff will rely on the data set, lots of data set, right? So this really rely heavily on the sensing. So yeah, I think sensing is very important. So it can be considered part of the overall system.
Okay, very good. Can we say, I think we have, so somebody said, thank you very much. It's a very interesting subject. I think we could have talked about another hour at least on this one, because I wrote down more than 20 questions. But we don't have time to go to that one. Just the last thing, I think RIS, I think more or less everybody mentioned that from different perspectives. Can we say RIS is a kind of electromagnetic sensing, and then we change the radio environment? Yeah.
Yeah, that's for sure. Not only for sensing, but it is electromagnetic, new transceiver concept that basically offers this electromagnetic information theory, new framework with lots of possibilities.
Okay.
Parameters to optimize. So yeah.
Thank you very much. That's all we had time, and I hope to see you around very soon. All the best. Thank you.